All right, so you've probably noticed it yourself. Python dictionaries just feel fast, almost like magic. Well, today we're going to pull back the curtain on that magic trick. We're going to find out how Python uses some really clever engineering to basically teleport right to your data. It's a question pretty much every Python developer bumps into eventually. You realize that grabbing a value from a dictionary with a million items is instantaneous. But trying to find something in a list of that same size, that could take forever. The secret, the reason for this incredible speed, is a data structure called a hash table. So this, right here, is the core idea for our entire explainer. With a list, you have to scan through, item by item. With a more complex structure like a tree, you have to walk down different branches. But with a hash table, you just teleport. You go directly to where the data is supposed to be. It is a total game changer for performance.
Yeah, I know, teleporting is a pretty big claim. It's not actually magic, of course, it's just some really clever math. And the engine that powers this teleporter is something called a hash function. That's the first piece of the puzzle we need to understand.
Think of a hash function as a perfect fingerprint generator for your data. You give it a key, let's say the word apple, and it spits out a very specific, very large number. Here's the crucial part. Every single time you give it apple, you get the exact same number back. This consistency is everything. So how does Python use that giant consistent number? Well, it's a simple three-step process. First, you start with your key. Second, you run it through the hash function to get that big integer. And third, this is the clever part, it uses the modulo operator, that little percent sign, to figure out which slot or bucket inside the dictionary's memory it should go in. This tells Python exactly where to put the data and, more importantly, where to find it later.
Now, this is a really vital point. The hash value for your key, that big number you get from hash apple, that never changes. It's stable forever. But the bucket it actually lands in, that can change if the dictionary needs to grow. So if your table size goes from 8 slots to 16, the final bucket for your key might move from, say, slot 7 to a completely new spot.
And right here, this is the million-dollar question. This is what everyone asks. What happens when two different keys, just by pure chance, happen to hash to the exact same bucket index? This is called a hash collision, and on the surface, it sounds like it would completely break the system, right? But this is the beautiful, intuitive answer. A collision doesn't mean the system fails. It just means you teleported to the right neighborhood, and now you might have to check a couple of doors to find the right house. When you compare that to walking the entire city street by street, which is what a list does, it's still unbelievably, ridiculously fast. Plus, Python is really smart about how it's designed to handle this. It intentionally keeps the hash table sparse, which is just a fancy way of saying it leaves a lot of the buckets empty on purpose. This makes the chance of a collision happening in the first place way, way lower. And when one does happen, Python just checks the next available spot in a predictable way. This is called probing, and since the table is so sparse, you almost never have to check more than 1 or 2 extra spots. Okay, so that leads to the next logical question. If Python has to keep the table sparse, it must have to resize it as you add more and more stuff. And you'd be right to think that resizing a massive table sounds, well, expensive. So how can we still say that adding things to a dictionary is fast? The answer is a really cool computer science concept called amortized cost. Basically, you might have one really expensive moving day where the whole table has to get rearranged. But that one expensive day is balanced out by the thousands and thousands of super cheap, lightning-fast insertions that happen all the other times. When you average it all out, the cost stays incredibly low. Let's just put it this way. Most of the time, adding an item to a dictionary is an extremely cheap, constant-time operation. In computer science, we call that O of 1. Then, once in a very great while, you have that expensive resizing day. But because that day is so rare, the average cost over time is still fantastic, keeping the whole system incredibly efficient. And remember, even during that big resize, the system is perfectly predictable. Python doesn't change the hash function itself. It just recalculates hash of key % new table size for every single item, safely moving them to their new homes in the bigger, better table. So we've used these analogies, teleporting, neighborhoods, moving days. That's great for building intuition. But now let's put some real numbers to it with big O notation. This is how computer scientists formally measure and compare the efficiency of different approaches. This scorecard really tells the whole story. Just look at that bottom row for the hash table. Lookup, insert, and delete are all O of 1 on average. That 1 means constant time. It means it doesn't matter if your dictionary has 10 items or 10 million items, the time it takes to find something is roughly the same. Now compare that to a list's O of n, where operations get slower and slower the bigger the list gets. It's not even a fair fight.
Now, of course, we have to look at the fine print. That O1 is the average case. It's what you get 99.9% of the time in the real world. Could you, in theory, create a bizarre scenario where everything collides and it slows down to ON? Yes, but you'd have to try really, really hard. And for inserts, that amortized O1 means that the cost of resizing is already baked into that incredible average.
And what's really cool is this knowledge goes beyond just dictionaries. You know Python's sets, which are amazing for checking if an item exists in a collection super fast? Or the counter object for counting things? Yep, they're both built on the exact same hash table magic. The same teleportation system is running under the hood. So let's bring it all the way back around and lock in this new mental model. The next time you're deciding what data structure to use in your code, remember this. A list makes you scan. A tree makes you walk. But a hash table lets you teleport. So to sum it all up, Python dictionaries and sets are so fast because hash tables let us jump or teleport directly to our data. The system handles growth smoothly by resizing, and it keeps collisions rare by keeping the table sparse. And the beautiful result of all that engineering is that amazing constant time O of 1 average performance. So now you have the theory. You get the why. The real fun starts when you use this knowledge to solve problems way more efficiently. Things like finding duplicates in a list or building a super fast cache. Now that you understand data teleportation, what are you going to build with it?